Have you ever used a ton of soap but just couldn't get a good lather? Or noticed that chalky white scale building up inside your kettle or on your faucets? That annoying problem is caused by hard water. It's full of dissolved minerals that cause trouble in everything from our homes to massive industrial plants. But what if we could tell those troublesome minerals, you're not welcome here? In this video, we're diving deep into the chemistry of water softening. We'll explore the core principle that makes it all possible: ion exchange. You'll learn about two powerhouse methods used in engineering to treat hard water. First, the classic zeolite method, and second, the ultra-powerful demineralization process. We'll break down how they work, how they're different, and we'll even solve a numerical problem step by step. By the end of this video, you'll understand exactly how we turn hard, problematic water into the soft, pure water that industries and households rely on every day. Let's get started. So how do we remove something that's completely dissolved in water? We can't just filter it out. The secret is to trade it for something better. This is the core idea of ion exchange. Imagine you have a pocket full of boring gray rocks, but you really want some shiny marbles. You find a friend who has a bag full of marbles and he hates marbles but loves gray rocks. You make a trade. You give him your rocks and he gives you his marbles. You both get what you want. An ion exchange resin does the same thing. It's a solid material that holds onto harmless ions. When hard water flows past it, the resin grabs the troublesome hard water ions and, in exchange, releases its harmless ions into the water. It's a simple, effective trade. Now, let's see how our first method uses this principle. First up is the zeolite process, one of the most common methods for water softening. Let's use our analogy. Think of the zeolite bed as a bouncer at a club, and this club is your water pipe. The bouncer's hands are full of friendly, harmless sodium ions. Now, hard water approaches carrying troublemakers like calcium and magnesium ions. The bouncer's job is to stop them. When a calcium ion comes along, the bouncer grabs it with one hand, and to keep things balanced, he shoves two of his harmless sodium ions out into the water. The water that gets past the bouncer is now soft. It doesn't have the troublemakers anymore. But eventually, our bouncer's hands are full of troublemakers. He can't hold anymore. This is when the zeolite is exhausted. To fix this, we need to regenerate it. We do this by flushing the system with a very concentrated salt solution, also known as brine. This strong brine solution forces the bouncer to let go of all the calcium and magnesium ions he captured, which get washed away. His hands are now free to grab a fresh supply of sodium ions, and he's ready to get back to work. The zeolite method is perfect for domestic water softeners, the kind you might find in homes to improve laundry and bathing. It's also widely used in smaller-scale industrial applications, where the goal is simply to prevent limescale buildup. The zeolite method is great for softening, but it doesn't actually reduce the total amount of dissolved stuff in the water. It just swaps one mineral for another. What if you need water that is almost perfectly pure? For that, we need a more advanced process. This brings us to demineralization, also known as deionization. If the zeolite process was a club bouncer, demineralization is a two-step, high-security checkpoint. First, the water goes to the cation exchange guard. This guard's job is to remove all positive ions, not just calcium and magnesium, but also sodium, potassium, everything. In exchange, he releases hydrogen ions, or H+. Next, the water flows to the anion exchange guard. Her job is to remove all the negative ions, like chloride, sulfate, and bicarbonate. In exchange, she releases hydroxide ions, or OH-. So what do we have in the water now? Just a bunch of H+ ions and OH- ions. And what happens when they meet? They combine to form pure, simple H2O, water. The result isn't just soft water, it's incredibly pure, demineralized water. Regeneration here is also a two-step process. The cation guard is regenerated with a strong acid to give it a fresh supply of H+ ions. The anion guard is regenerated with a strong alkali, like sodium hydroxide, to resupply it with OH- ions. This high-purity water is absolutely critical in many industries. You'll find demineralization plants in pharmaceutical manufacturing, where even tiny impurities are unacceptable. It's essential for the electronics industry to wash microchips, and it's used to produce feed water for high-pressure boilers to prevent any corrosion or scaling. All right, let's put this theory into practice with a numerical example you might see in an exam. Problem: a zeolite softener becomes exhausted after softening 10,000 liters of a hard water sample. The softener is regenerated by passing 200 liters of a 10% NaCl solution. Calculate the hardness of the water sample in ppm. Don't worry, we'll walk through this together. Step 1. Find the total amount of NaCl used for regeneration. The problem states we used 200 liters of a 10% NaCl solution. A 10% solution means there are 100 grams of NaCl in every liter of solution, so the total mass of NaCl is 20,000 grams. This is the amount of salt it took to kick out all the hardness-causing ions from the zeolite. Step 2. Find the calcium carbonate equivalent of this NaCl. In water chemistry, we measure hardness in terms of a standard compound, calcium carbonate, or CaCO3. We need to figure out how much hardness is equivalent to those 20,000 grams of NaCl. From chemistry, we know that 2 moles of NaCl are chemically equivalent to 1 mole of CaCO3. The molar mass of NaCl is 58.5 grams per mole, and for CaCO3, it's 100 grams per mole. So, 2 times 58.5, or 117 grams of NaCl, is equivalent to 100 grams of CaCO3. Now we can set up a simple ratio. This means that 17,094 grams of hardness were removed from the water in total. Step 3. Calculate the hardness per liter. This total hardness was removed from 10,000 liters of water. To find the hardness in 1 liter, we just divide. The hardness is 1.7094 grams per liter. Step 4. Express the hardness in ppm. The standard unit for hardness is milligrams per liter, which is the same as parts per million. First, let's convert grams to milligrams by multiplying by 1,000. 1.7094 grams per liter becomes 1,709.4 milligrams per liter. And since 1 milligram per liter is equal to 1 ppm, our final answer is 1,709.4 ppm. And that's how you solve it. The key is to relate the regenerating chemical back to the equivalent amount of calcium carbonate. So let's do a quick recap. The zeolite method is like a bouncer. It grabs the hard water ions, calcium and magnesium, and trades them for harmless sodium. It gives you soft water and is regenerated with salt. The demineralization method is like a high-security checkpoint. It removes all positive and negative ions, replacing them with H+ and OH-, which combine to form pure H2O. It gives you demineralized water and is regenerated with acid and alkali. Understanding these two methods is fundamental to water treatment in chemical engineering. I hope this explanation made these complex topics feel simple and intuitive. If you found this video helpful, please hit the like button, subscribe for more engineering content, and let me know in the comments if you have any questions or what topic you'd like to see next. Thanks for watching, and I'll see you in the next video.